Non-volatile memories are an exciting choice as a main memory because of its many alluring features, but because of their non-volatility, they are vulnerable to data remanence and cold boot attacks, making the non-volatile memory very insecure. If we want to secure the memory, we need to encrypt all of its contents using counter mode encryption, and also we need to have the Merkle tree to protect the integrity of the counters. But the counters and Merkle tree nodes are cached inside the processor. Since caches are volatile, cached contents are lost during a crash, leaving just some stale values in the memory. If we want to make our system crash consistent, we need to have a mechanism to recover the counters as well as recover the Merkle tree. The counter recovery can be achieved by various means. One state-of-the-art work, Osiris recovers the counters using ECC sanity check. And for the Merkle tree, after recovery of the counters, we can recreate the entire Merkle tree by recalculating the intermediate nodes up to the root. Now let's look at how the recovery process might look like. Here we have our encryption counters and also the Merkle tree nodes stored inside the non-volatile memory. If a system crash happens, we're going to lose all of the modified values from the cache and have some stale values in the non-volatile memory. But after the crash, our processor does not have any idea which counters or which Merkle tree nodes it has lost from the cache. So it has to treat all of the memory blocks, the counters and the Merkle tree nodes as a stale. If we use Osiris or any other counter recovery scheme, it needs to read all of the data and their associated counters one by one to recover them. After the recovery of the counters, we can recalculate the hash values of the Merkle tree intermediate nodes and recover the system level by level. Here we can see how the recovery time increases with the increase of the size of the memory. For example, if we use 8 TB memory, we'll have to wait for 8 hours for the recovery of counters and Merkle tree nodes. Besides, SGX-style parallelizable trees have their own counters in intermediate nodes that are lost during the crash and are not recoverable at all unless we use strict persistence, which incurs 10 times extra writes. For general non-parallelizable trees, our solution Anubis has both low recovery time and also lower performance overhead. And also, for SGX-style parallelizable trees, Anubis is the only practical solution to recover the system. For more details, please attend our presentation Monday, June 24, 2019 at 2 p.m. Session 2A, Memory and Storage. Thank you.